All right, so here we are, ready for another week's exciting lecture. We're going to talk this week about a really important type or genre of statistical models used to model time series data, referred to as decomposition models or seasonal decomposition models. Now, at least initially in their early conception, these seasonal decomposition models were um, maybe a little bit unusual, certainly for modern day statistics, based a little bit less on mathematical theory and more on kind of intuition, simulation, empirical validation. They just sort of seemed like a nice way to work with, to model, and as we'll see, perhaps even most importantly, to represent, in particularly visually, to make plots of of data that have some sort of seasonality to them, right? We talked about this notion of seasonality last week. That said, without the theoretical foundation, they have been shown to work well in real life empirical settings, so much so that they are used quite frequently, and over time have sort of developed you know, a more rigorous mathematical foundation to make these models even stronger. Right. In fact, this type of methodology, this type of approach, again, particularly from like a graphical or visual um, standpoint or framework, is used by a lot of governments for government data, right? Because a lot of government data is essentially time series data. And our own Census Bureau, for example, the U.S. Census Bureau, uses advanced versions that we're going to talk about this week. We're kind of scratching the surface a little bit, and I'll talk a little bit in the last few slides about how we might go deeper if we were interested in doing that. But the U.S. Census Bureau uses kind of advanced, fancier versions of what we're talking about this week to model all the different national time series that they need to model, and they even go and they export the software that they use to other countries, so other countries, using the same software, are essentially following suit. SAS has a version of that software that we're talking about here, and I'll talk about how we can access that in SAS towards the end of this lecture. Now, one of the key ideas to seasonal decomposition, and in reality, it's a key idea to time series analysis more generally, is this idea of a moving average, sometimes referred to as a rolling average. Um, and the idea behind a moving average is, well, we'll talk about it next slide. But moving averages feed into something referred to as smoothing a time series. And these are both like really big ideas in the broader field. More specifically, we could use them to seasonally adjust, right? That's the term that you use a lot. I find it like linguistically confusing. You may not, but seasonally adjusting is really referring to like deseasonalizing our data. So what you could think of, like, if you made a graph of our data, that graph might in some way look noisy, and right, that the noise could be coming from a number of different sources, but one of those sources might be some underlying seasonality. And so this idea of seasonally adjusting, aka deseasonalizing our data, is kind of removing that noise, right? Removing that seasonal noise, so we might be able to look more clearly at underlying trends. And this really, these ideas, these moving averages, this smoothing, this deseasonalizing of data, is really kind of like the heart and soul of the seasonal decomposition approach that we're talking about right now. Now, the basic idea is this, right? Seasonal decomposition, right? Decomposing is breaking something into smaller pieces. So what we're going to do is we're going to take an overall time series model. That model is built up of different pieces. We actually looked at something similar to this last week. Generally, or most broadly, we're going to look at a time series model as having 4 potential components to it. Those 4 potential components are going to be an overall trend, some sort of seasonality or seasonal factor, a cyclical factor, and then like an irregular factor. We could think of that irregular factor as like the error term that we're used to from, from our basic linear regression class. Oh yeah, here we go. So the trend, right, here's our 4 pieces. We're conceptualizing a statistical model built out of these 4 pieces. The trend is like an overall parametric trend, like from a linear regression class, like some kind of often polynomial trend, right? So we often might consider like no trend. So this would just be like a flat horizontal line, like essentially just like a y-intercept. A linear trend, so something that's linear in time, or a quadratic trend, right? Could be trending up, could be trending down in a quadratic fashion. Could be actually, I guess, trending both ways, right? Kind of starting up and then trending down, or starting down and then trending up. We have a seasonal factor. So seasonal factors are consistent from year to year. We have a cyclical factor. One of the underlying themes is that the cyclical factors are extremely difficult to fit. I'm including them just to kind of present this model in its most general form. But it's extremely hard, and because of that, pretty rare to model cycles or to include cycles in our model. What are these cycles that we're talking about? Probably like the most common one would be like a boom or bust cycle, right? Inflation, recession, things along those lines. And you know that we do have those kind of ebbs and flows in the macro and micro economies, but it is hard to predict them. And even though we might say like, it's roughly every 5 years, it's not perfectly every 5 years or every 7 years or whatever you might try to estimate it. And because of that irregularity, it's extremely difficult to accurately estimate cycles. Sometimes cycles play maybe a more easy to model part in say like meteorological data. So again, I'm not a meteorologist, so I may be speaking out of turn. But you have things like El Nino, El Nina, which I think are like these sort of storm fronts that come around every X years. And so I think weather might have some of these patterns. Maybe maybe like solar eclipses, sunspots. I don't know. There might be like solar phenomenon that have like a regular pattern. And so things like that could be represented with some sort of cyclical component. And then the 4th component is going to be the irregular term, the error term. And that error term is just sort of everything else, right? All the sort of other components that are not in our model, but nonetheless reflect our dependent variable y, right? These things can be stuff like war, strikes, famine, technological innovation, so on, etc. Now, one thing to keep in mind, and this is a limitation in our model. Typically, these models are assuming that the factors are not changing over time. That is, August has the same impact on, I don't know, for example, maybe our y variable is the population of adorable meerkats. Man, it was a while ago, but did any of you watch that cute little show, Meerkat Manor? Oh, such an adorable show. Our model is assuming that August impacts the population of meerkats the same regardless of what year it is. And with like global warming and climate change, that's maybe not a realistic assumption. It might be that progressively more recent Augusts having a increasing impact on that population because of global warming or climate change. And if that's true, our model is not capturing that. That said, right? I mean, on some level, we are doing it. We are taking it into account. It's just being done in like that irregular term. It's being instead in our error term. Our error term could still be used to capture things like a quote unseasonably hot August. But right, our goal, remember statistically, is always to make that error term, that irregular term, as small as we possibly can. And so if there is variation in Augusts and how August impacts our Y variable, and we're not modeling it, it's making our error term larger than it maybe needs to be. And so how do we get around this? That's something we're actually going to talk about next week. Next week we'll talk about something called exponential smoothing. And exponential smoothing is a type of modeling that allows us to have these parameters, right? They say the August seasonality effect changing or adapting or mutating over time. All right, so here we are. We've kind of set the stage. We have our model. It's built of these 4 pieces. And so what's our goal? Well, our goal is to estimate these pieces. In particularly, our goal is to estimate the trend and the seasonality. Those are usually the 2 things that we are most interested in estimating. Broadly speaking, we could, in theory, try to estimate a cyclical factor if we knew the length of the cycle. Again, not often appropriate in practice. And so how do we go about doing this? Well, we'll look at all these different steps, but the big picture idea is that we typically assess our trend by removing the seasonal factors. This idea, kind of already insinuated this in some earlier slides, this idea of removing the seasonal factors is known as deseasonalizing our data. Now we're going to consider 2 types of models. One is a multiplicative seasonal decomposition, and this is used whenever we have increasing or decreasing seasonal variation. Now notice this was something that our models from last week could not accommodate. So it's going to be, I'm going to make this kind of the focal point of this week's lecture. But we can also apply seasonal decomposition to the situation where we have constant seasonal variation. In this case, we would just use what's referred to as an additive seasonal decomposition model. So we're going to focus on the multiplicative, and then we'll spend a few slides after it seeing like the additive model is pretty similar, pretty analogous to the multiplicative model. You just do kind of a few tweaks. We'll talk that over. But our focus is going to be on that first one. So here is what our multiplicative decomposition model looks like, right? Our dependent variable y, right? What's our dependent variable y? Could be the stock price at time t, could be inflation at time t, could be the number of COVID cases at time t, could be right, the velocity of a river at a certain point at time t, right? Lots of different things that y could be. And it's a product of a trend, seasonality, potentially a cyclical component, although as I said, often we kind of omit that term, and that error term, right? We call it IR. Textbooks, I think, calls it IR for irregularity. And in our regression class, we were calling it E for error, playing essentially that same role. And again, right, worth re-emphasizing, we have this time independence in our model. The parameters of the factors are not changing over time. This applies not just to the seasonality, which is what I highlighted previously, but it's also true of the trend. right? That is, we're assuming that linear trends don't turn quadratic. We're also assuming, right, that linear trends stay constant. Now, right, for a long enough period of time, that's almost guaranteed to be unrealistic. That's what we talked about in that first week of class. We talked about the dangers of extrapolation. So we want to keep that limitation in mind. It is a pretty important one. Probably, hopefully, it's not a huge issue when we're working over data over a short range, or at least predictions over a short range of values. But right, as we extrapolate farther and further and further into time, this idea that we're assuming this linear trend persists, or we're assuming this quadratic trend persists in the same way, becomes probably, right, less and less realistic. Now, I just wanted to show, right, how a multiplicative model works for us. It's a little bit unique. Um, we do some similar type modeling in the logistic regression class, which you may or may not have taken. We don't do examples of multiplicative models in our linear models class. So if you're coming just off the linear models class, right, this might be something a little bit new to you. So let's kind of look through a little bit of a simplified example. Right, in here our y variable is sales of a particular brand of coffee every quarter. And let's say that sales are good, right? That in general, our sales are trending up. That is, our underlying trend is 25 plus 10 times t. T is time. Right, so you could almost think of our sales as like, right, they started at 25. That was like our baseline sales. And here our t is our time is quarters. We're looking at quarterly data. So every 3 months, our sales have been increasing by 10 units, right? Whatever that is, $10,000 or tens of ten thousands of dollars, or maybe we're just talking like 10 units, where units is just, right, a certain amount of coffee. And in addition to that trend, we have that seasonality because, right, demand for coffee sort of fluctuates with the seasons. So seasonality one, the first quarter. What's first quarter? It's January, February, March, right? Those are some cold months. So cold months, right? The coffee demand is a little bit higher than expected, right? 30% higher than expected. Then we start hitting the springtime months, right? The weather's kind of warming up. Coffee demand starts to diminish. People are maybe a little bit more interested in, I don't know, something nice and cold like lemonade. And so now, right, we're at 70% of what's expected. Right? We take that trend, we multiply it by 0.7. It's reduced. That seasonal demand in the second quarter is less than we might expect. Right? Then we hit those summer months, right? So what would be the third quarter would be what? July, am I doing my months right? Yeah, July, August, September, right? Some of the hottest months out there. And so now, like, coffee demand is very much suppressed, right? It's half of what we might expect. But then we start transitioning into like the colder months. Now we're getting into the fall. Oh, peppermint coffee? No, what am I saying? Pumpkin spice coffee? I'm not a big coffee person. Pumpkin spice comes back. Everyone gets crazy, right? Now our sales are 1.5 times what we would expect them to be. Right, so we see a significant boost above and beyond, right, what the underlying trend, right? You think of that underlying trend is kind of like the success of our business model, and that seasonality is just sort of like how the seasons or how the quarters are adjusting, right, changing that overall model success. Right, and this is how we might here's how we can actually apply that model. So if I wanted to get an estimate, and here we're assuming no cyclical component. So this is a little bit of a simplified model. We're looking at expectations, so that error term kind of goes away, and that irregular term. And so if I wanted to look at, like, okay, how many sales do I expect at quarter one? How many sales do I expect for quarter two? How many sales do I expect for quarter three, quarter four? And then now it's right, what, quarter one of the next year? So like our 5th time point, our 6th time point. And then hopefully you could go back to that model from before, right? Our underlying model, our linear trend was 25 plus 10 times t. So I'm just plugging in our time point now. And then I'm multiplying that by the seasonal factor. So, right, that's a repetitive process. I do 1.3, then I multiply by 0.7, then I multiply by 0.5, then I multiply by 1.5, then I multiply by 1.3, right? I repeat the process, right? Now I multiply by 0.7 because, right, time point 6 corresponds to the 2nd quarter. You could program that, right, in SAS. You could program that in a spreadsheet. Might be a fun kind of side exercise for those of you looking for a little bit of self-growth, and extend that even further, right? Maybe 10 time points, maybe 20 time points. And if you do, by looking at those numbers there, right, we can maybe see, like, not only are the numbers growing, but like that variation is growing as well, right? Look at the difference between time points 1 and 2, right? That difference is essentially 14. If I look at the difference between time points 5 and 6, right, that 14 becomes what? A difference of 38. So overall, the gaps between these things, the variation in these observations is growing, and that's a natural byproduct of this multiplicative model, right? As the underlying trend is growing, it's being multiplied, and that growth gets multiplied, increasing or kind of blowing up the variation. All right, so hopefully this gives like a little bit of sense how the models work. Maybe we can look at that and get an intuition about like why this multiplicative model is giving us, right, this increasing variation. But again, if you really are having trouble seeing it, then I would encourage you, right, extend what I've done to time point 7, 8, 9, 10, throw it into SAS or Excel, make a little plot, a good kind of lab type exercise, and see for yourself like what this plot looks like. All right, so that kind of shows us a little bit how the model works. Let's talk now about estimating that model. So there's a number of steps. Man, I want to say 5-ish. And the first step is this. The first step is that we go about and we calculate something referred to as a moving average. So assuming that there are L periods per year, right? So we're talking about quarters, that L is going to be 4. We're talking about months, L is going to be 12. We have L periods per year. We can compute the first moving average as the sum of the y's for the first L observations divided by L. And then the second moving average is, all right, we start at the second observation and we sum all the way to, let's say that we're looking at monthly data. So we would be summing all the way to the 13th observation and then still dividing by 12. Then the next moving average, as we start at time point 3, we add all the way to time point 14, divide by 12, right? And we just keep doing that. This kind of rolling moving average. So, right, the first one, if we're talking about monthly data, that first moving average is what? It's like adding January through December. and dividing by 12. And then the next one is what? It's not starting at January. Now we're starting at February. Now we're adding February through January, dividing by 12. Then we're adding March through February, dividing by 12, right? And we go as far or as long as we can. And that gets us our moving averages. Now, unfortunately, when we're working with even L's, which is most of the time, we have this kind of weird kind of like bookkeeping problem. And the bookkeeping problem is this. Well, here, so we can see it pretty easily by looking at this example. So if L equals 4, we're working with quarters, and so our first moving average would be what? Y1 plus Y2 plus Y3 plus Y4 divided by 4. Now, if I look at that, I can see that that moving average is essentially centered at time point 2.5. That's a weird kind of like bookkeeping issue, right? It's centered between 2 and 3. And do we see that we would not have this problem if we were working with L equals 5? So this is a kind of problem that's created by the fact that most of the time we're working with even L. That we just tend to do time periods in even increments. Right? If L equals 5, which again in practice would probably never happen, but if L equals 5, I would have, right, Y1 plus Y2 plus Y3 plus Y4 plus Y5, and that would be centered at Y3 or time point 3. That would be nice. But when I'm working with quarters, right, I'm centered at time point 2.5. And then my second moving average, that's Y2 plus Y3 plus Y4 plus Y5, right? That's sort of centered between 3 and 4, or we might say at time point 3.5. Right. So first thing to observe, and I think I'm going to make this more explicit in the next slide, is that these moving averages, it's hard to allocate them with a particular time point because they sort of fall between two time points. We should also observe, like when we're looking at this thing, that every quarter is always represented in each moving average. And because of that, what we can see that we're doing is we're essentially averaging out the effect of seasonality as well as randomness, right? Do we see that? So by adding up one observation from every quarter, we're averaging out the effect of quarter, right? Some quarters are more than expected, some quarters are less than expected, but by adding all of them together, we're averaging out that seasonal effect. And, right, just in general, anytime you're adding up anything and creating an average, you're averaging out random noise, right? That pure randomness, that error term. So our moving average has removed or averaged out the effect of seasonality and randomness. It's an important idea, maybe worth writing down on a piece of paper next to you, because we are gonna revisit that. Now here's step 2. Step 2 is like a kind of like an awkward bookkeeping step, right? So, right, we had this moving average that was centered at time point 2.5. We had a moving average that's centered or anchored at time point 3.5. Of course, these aren't real time points, and so we would like to have some value that corresponds to an actual point of time. And so what do? We get that by averaging our moving averages. That is, if I take the moving average for 2.5, I add to it the moving average of 3.5. Now that's centered at time point 3, right? So I add those up, I divide by 2, I have a centered moving average, CMA. that now is anchored appropriately at time point 3, right? So like it's a little bit of like an awkward step. The moving average is like conceptually the most important piece. This is just like a little something that we have to do to like make that line up with our time variable. So now we have the centered moving average. It has averaged out the effects of seasonality and the effects of our irregular term. And so because we've done this, right, because we've averaged out the effects of that seasonality and randomness, right, the centered moving average is just now the trend times the cycle. Right? Do we see that? We've removed seasonality, we've removed randomness. So our centered moving average at time t is mathematically going to be just our trend times our cycle. Now again, we often don't have a cycle, so often our CMA could just be an estimate for our trend. Now, I said this before, making it more explicit here, right? Step 2 is unnecessary if we're working with a situation where L is odd. Trimesters, right, would be an example. I don't know that you see trimesterly data very often, but that would be like L equals 3. We would not need to do a centered moving average. And there are other instances. I think I'll probably give you a homework assignment or a lab assignment actually that where you look at a real life analysis in a situation where the researchers kind of cleverly set up the problem in a way that the L ended up being odd, and so that saved them having to do this this extra step. All right, so now it's just like a little bit of like mathematical sleight of hand, I guess you might say. We get to look at all the different implications of this. So we can get now an estimate of our seasonality and the irregular term. Our goal is to get the seasonality, but this step like 3A is going to get us the seasonality and the irregular term, and then from there we're going to remove the irregular term, right? So our goal with step 3 is to get an estimate of seasonality. So we get an estimate of seasonality first by just kind of isolating or extracting that seasonal times error, seasonal times irregular term, and we can get that by taking our original observation y sub t, right? So remember, write this out if you need to. Write it out on a piece of paper right next to you. Remember, our y sub t is what? Our y sub t is built of, it's a product of 4 pieces, right? Y sub t is the trend times the seasonality times the cycle times, right, that irregular term, right? Y sub t is a product of 4 things on top. We said on the previous slide that the centered moving average is what? It's the trend times the cycle. So if I take those 4 pieces on top, I divide by the centered moving average, that cancels out the trend, that cancels out the cycle, and I'm left with exactly what's on the left-hand side of that equation. I'm left with a seasonal times irregular term. So that's like step 3A, right? We've isolated the seasonal term. Admittedly, there's still some extra noise because of the irregularity or the errors. So our next step is going to be to get rid of those errors. Yeah, here it is. So now we can get an estimate for the seasonal effect by averaging all observations in the same time period, right? So for example, if we had monthly data for say 2005, 2006, 2007, then we could get an estimate for the seasonality of August by adding that seasonal times irregular piece for August 2005, plus that piece for August 2006, plus that piece for August 2007. We add those 3 pieces up. we divide by 3, right? Just because there's 3 observations. So, right, if I had 4 years of data, I'd be adding 4 numbers and dividing by 4. If I had 5 years of data, I'd be adding all 5 of those and dividing by 5. And what we're doing here is we're essentially trying to remove that error term, right? That error term is, right, maybe the unseasonably hot or unseasonably cold Augusts that may have occurred over the period of time that we observed our data. And so once we average out those irregular terms, we now have an estimate for our seasonality. Right, which is good for a few different things, but maybe most importantly, it's just nice from like a descriptive perspective, right? It's just nice for us to be able to quantify like how the seasons do impact whatever phenomenon it is that we're studying. Right? So already, right, just having the seasonal piece is very nice just from like a descriptive standpoint. Now again, like this kind of like bookkeeping thing, this typically does not actually change your seasonal estimates very much. It's usually a very minimal thing. We ideally like we ideally like all the seasonal effects to have like an average of 1. Because what that's basically doing is it's like forcing those seasonal effects to fluctuate around a true trend, right? That is, if like one of my things is like a 1.5, we kind of want it to be balanced by a 0.5, right? Which means like if I added those 2's up, I get 2, but then I divide by 2, I get 1. I want their average to be 1. And that it's usually pretty close to that, but it doesn't have to be that. In fact, often is not it exactly. And so just to kind of make it a little bit nicer in that sense, we do this kind of normalizing here. This little extra step, this seasonal adjustment. All right, so once we have our seasonal estimate, we could now deseasonalize our data. And we deseasonalize our data by creating some deseasonalized version of our variable of interest. Let's call it D for deseasonalized. And we do that by taking our original observation Y and just dividing by the seasonal term, right? So dividing it by that seasonal term is literally canceling, literally removing the seasonal component from our Y. I can now plot the deseasonalized data, and doing so should show me what the deseasonalized trend looks like. And then once I know what that deseasonalized trend looks like, now I could use regression techniques to estimate it or fit it. Yeah, right. I could create a scatter plot again, just like in our 512 class. I could create a scatter plot to estimate the trend. So I can look at that scatter plot, say, does this look linear? Does this look quadratic? Does this look exponential? Once I've decided that trend, I can now fit that trend with the appropriate procedure, maybe a proc reg, maybe a proc GLM. That is, for example, if I look at the plot of the deseasonalized data and I think I see a linear trend, then I would think that, right, D sub T, the deseasonalized data, right, looks like this linear model, and I would then use proc reg to solve for that beta naught and that beta 1. All right. So that's really like the 2 big pieces. The 2 big pieces are, right from a descriptive standpoint, figure out our seasonal terms. That describes how the seasons may or may not be affecting, right, my business. And once I have that seasonal term, I could deseasonalize the data, which then allows me to use like 512 type techniques to estimate the underlying overall trend. those are usually the two big steps that I'm working on. We'll talk in a little bit about how to combine those things to do extrapolations, right? How do I take this information, these seasonal components and this underlying trend? How do I combine them in such a way to generate predictions? We'll talk about that in a second. But before we do that, we have this sort of step 5, this kind of leftover step. Included for completeness, typically not really of a lot of interest. But once we've completed steps 1 through 4, we could, if we wanted to, then compute estimates for the cyclical term, which again I said in practice is seldom done, or the irregular term and the irregular term, right? And we do so in the following way, right? If I take my y sub t and I divide it by the trend times the seasonal component, right? Because I have both of those now. I estimated those in steps 3 and 4. If I do that, I have an estimate of the cyclical term times the irregular term. Again, I could create a sum to average out the irregular term. That now gives me the cyclical term. And then if I divide, right, that's CL times IR. If I divide that by my estimate for CL, then that will give me like the IR, which I could think of as like my residuals. Again, like, you know, it's there for completeness, but this step 5 is typically not of interest or utility. Yeah, right, because often we don't have enough data for accurate predictions of a cyclical factor, right? As even if we knew, right, even if we knew like exactly like how many years or how many time points this underlying sort of macro cycle is, we often don't have enough data to predict that. So even in like the best case of this kind of omniscient knowledge of a predictable cycle that in many cases doesn't exist, even if we had all that, we typically don't have enough data to accurately estimate it. All right. So just a couple more things. First, I want to talk about how we use this information to generate a forecast. So that's what we're going to do right now. And then I want to walk us through like an actual example, like how would we do this in SAS? What would it look like with some actual data? So those are the kind of the next two things that we're going to do. And then we'll talk about how we could adapt this process, right? How this process would tweak a little bit, how we could tweak this process to accommodate additive models. All right. So first off, how do we do a forecast? Well, if a well-defined cycle exists, we're going to predict for some future time point t. We just do the trend times the seasonality times the cyclical component. In the more common case where there's not a well-defined cycle, we haven't estimated it, then we're going to generate our prediction. We just generate the trend for some future time point t, and we multiply it by the appropriate seasonal thing. That is, if what we're predicting for falls in the second quarter, then we multiply it by the seasonal term for the second quarter. Now, typically in 512, right, our prediction intervals are based off this like t distribution, and or f distribution, and they're done with this, you know, this theoretical foundation that has all these like assumptions, right, that we talk about in 512, and of course, depending on how well these assumptions are satisfied, that's how justified our prediction intervals are. Things are a little more loosey-goosey, at least with like your beginners seasonal decomposition models. And so what's typically done in practice is we look at, we derive our prediction intervals by looking at the prediction interval margin of error, which is computed by SAS on our deseasonalized data. And then we apply that margin of error to our estimate, to our prediction, which has been seasonalized, right? It's a little tricky to put in words, but we'll do an example real soon, and hopefully when you see the example, you'll see the process is pretty straightforward. Yeah, so here's our example. I took it from our textbook. I like our textbook a lot. My one complaint to it about it is right, it has a lot of fabricated data sets. In some cases I use them, in some cases I don't. There is an advantage, right? There are advantages to fabricated data sets. Especially when we're like learning something for the first time, it is nice to have like a pretty simple, straightforward data set that works really nicely, so we can kind of, see how this works in like an optimal setting. And then that'll give us like a nice springboard or foundation for, some of the more real life, potentially messier data sets we're going to be working with later in the semester. So all these generic names. We have the Discount Soda Shop Inc. Um, allegedly owns and operates 10 drive-in, yeah, soft drink stores. Discount Soda has been selling Tasty Cola. Oh man, I could really go for a nice cold bottle of Tasty Cola right now. I am getting parched. I do these lectures just straight through these days, so yeah, man, I forgot to get myself a bottle of Tasty Cola. A soft drink that was introduced on the market just 3 years ago. You may or may not have heard about it, but it has been gaining in popularity. And so this data set of the fictitious soda company is looking at 3 years of monthly sales in units of hundreds of cases. All right. So here's a plot of our data. All right, 3 years worth of data, 2005 to 2008. We can see what? We can see, so hopefully what our eyes are seeing there is that it does look like a repetitive seasonal pattern. Probably not surprising. It looks like the peak is always what? The peak is always those summer months, right? Because man, when it's hot outside, nothing goes down better than a nice cold tasty cola. But we also see what? We also see increasing seasonal variation. Agreed? Right? This idea here is that like that difference from like trough to peak, trough to peak, trough to peak is growing. Right? That is, it's not stable. There's variation in that. And so that tells us that a multiplicative seasonal decomposition model is appropriate. Right? We see a seasonal pattern A, and the variation of that seasonal pattern appears to be increasing. So that tells me I want to use a multiplicative seasonal decomposition model. Well, I think I just gave our thoughts, right? So our thoughts were that it looked like it looked, and again, this is one of those things where it's like, yeah, if I were to go back and look at that thing, it also looks like it has a nice linear positive slope to it. And so like in a situation like that, the deseasonalizing becomes like a little bit less necessary. That is, like the underlying linear trend is like pretty apparent. But still, right, if I wanted to estimate exactly what that trend is, I would need to deseasonalize the data. So it's like I don't necessarily need to deseasonalize it to see the linear trend, but I would need to deseasonalize it to accurately estimate that seasonal trend. And I would also like to say, and we'll see this as we move through the course and as we look at, right, more complicated data sets, that there are absolutely situations where the data is messy enough that it's not easy to just like eyeball like the original data set and say, yeah, that looks linear or that looks quadratic. And in that situation, like deseasonalizing becomes even more essential. So how do we do all this? Well, it turns out that we can do seasonal decomposition in SAS through something called proc time series. So proc time series, right? We specify the name of our data set. Here it's data equals cola. We're going to output the results into a data set. So I do that by saying out decomp, and then I just name my data set. I can name my data set whatever. Here I'm calling the outputted data set decompose. Proc time series requires requires a time variable, and we specify that time variable with the ID statement. So our time variable is date. So I would do ID date. I have to communicate to SAS what the interval is. In this case, it's monthly data, so I say interval equals month. If it was quarterly data, I would say interval equals quarter. I'll talk about what that accumulate statement's doing. We're actually not using it in this case, and in a lot of cases we won't use it. But still, you get an error, I think, if you don't put it in. So I wrote it in there, accumulate equals total. I'll talk about that in a slide or two. I say decomp because that's what I wanted to do. Proc time series can do a lot of different things. Here I want it to do seasonal decomposition. So I do decomp / mode equals molt. If I wanted to do additive decomposition, I would do mode equals add. And then I specify what my variable is, my dependent variable. In this data set, it was just y. Okay. One thing to keep in mind, and it might be worth going back to your 511 notes to kind of refreshing yourself on this. Proc time series does require your date variable to be in a date format, right? So in 511 we talked about different types of in formats and variable formats. I know in 511 you do talk about date formats quite a bit. Now, admittedly, that might be a while ago. Proc time series does require that your time variable have that date format. The accumulate option is required syntax, even though we don't need it in this example. What the accumulate option is basically doing, it's telling SAS like what to do. If you had like multiple observations for, say you had like multiple observations for August 2005. And when we said accumulate equals total, it's basically saying if you have multiple observations, just add all of them up into just a single observation for August 2005, right? Which is probably what we would do in most cases. And if for some reason you just wanted to put the results on your screen rather than a data set, you could just do print equals decomp, and it will put the results on your screen. Now, most often we want the output in a data set. Why? Think about it for a second. Why do we want that? Exactly, right? One of those steps, what was it? Maybe step 3-ish? Maybe step 4. Step 4 was what? We had to get the deseasonalized data and we had to plot it, right? So I want that deseasonalized data outputted so I could use proc plot to then plot it, and then after doing that, after using proc plot to plot it, I'm then going to use proc reg or proc glm to fit it, right? So I need to output that deseasonalized data so I can then manipulate it, which is why outputting it to a data set is what I would typically do in practice. So here's a proc print of what that data set looks like after I run my seasonal decomposition. Right, I didn't specify a cyclical term. I have my dates, right? So they're in that date format, January 2005 to December 2007. I can see, right, every observation has a seasonal component, 1 through 12, 1 through 12, 1 through 12, just saying what month it is we're working with. I have the original underlying data. I have the TCC. TCC is essentially the centered moving average. So I have the centered moving average. I have the seasonal component. I have the error term. And I have the deseasonalized data finally. That's like the one that I probably care about that most, right? SA for seasonally adjusted. I have my seasonally adjusted data, aka my deseasonalized data. My D sub T is that rightmost column, All right, so the columns I probably care about the most is the SC, that's my seasonal components, and the SA, that's my deseasonalized data. So again, from a descriptive standpoint, I can look at that seasonal component and I could see how different months are going to affect my soda sales. Now remember, these are a multiplicative effect, right? So the seasonal estimate for January is what? It's 0.49327. That's about 0.5, right? So basically, soda demand is depressed in January. It makes sense. It's a cold month, right? Soda sales are about half what we might expect them to be. And then in February, they're about 60% of what we might expect them to be. March, pretty similar. So like it looks like February and March have about the same seasonal effect. April, they're about 68% what we expect them to be. May, they're about 56%. Then we get to June, they're right about what we expect them to be. Excuse me, because that June estimate's pretty close to 1. July though, now, right, we're getting into summer and we're starting to see our soda sales start to spike. Oh man, everyone loves Tasty Cola in the summer. So we got 1.467, so it's about 1.5, so it's like, about 50% more than I would expect it to be. And then about 1.7, so about 70% more. And then, right, September, Tasty Cola is about twice as much as I might expect it to be. And then the months start getting colder, so like that effect starts to subside, right? And then, of course, I get to observation 13. Observation 13 corresponds to January, so that seasonal effect, right, that 0.49327 is the same as it was for observation 1. Okay. So again, hopefully we can see there's some descriptive value to the seasonal components. Now let's go ahead and look at the deseasonalized values, that D sub t, which corresponds to the SA variable. Yeah, I mentioned that TCC is our centered moving average. So a look at our underlying trend. Right, so here's my plot of that SA, my plot of my deseasonalized data. Look at this now, right? The trough, the up and down, the seasonal pattern has in fact been removed, right? I have removed that seasonality. I have deseasonalized it. Again, sometimes it's referred to as seasonally adjusted. To me, that always, right? To me, seasonally adjusted sounds like you're adding seasonality into it. That may or may not be how you interpret that phrase. So I try to avoid it, but that is used in practice. They mean the same thing. My deseasonalized data looks less messy. I look at that as suspected. It looks like a relatively straight upward sloping line. Now, what's the slope of that line? What's the y-intercept of the line? Well, I could find that out with a simple proc reg. So here I do proc reg, data equals decompose, model SA equals time / CLI. Remember proc reg, CLI will give us our prediction intervals. So we'll see how to generate a forecast. That's our goal. Our ultimate goal is to be what we have 3 years of data. We have 3 years of data. So we'll do a forecast for time point 37 for January of year 4. Now I think before our time variable I used date. Here I switched it to t, where t is just like observation number 1 through 36. And that's because you can make it work, but proc reg has like a little bit of a hard time with the date variable. It has a hard time using variables that are in a date format. So here, proc reg does better when you're giving it like a 1, 2, 3, 4, 5, 6. So I set it up that way. So just to give you a heads up that there was a slight change of, I wouldn't say a change of variable, but a change of how we represent that variable. Okay. So here's my proc reg. I can see that the estimate for the y-intercept is 380.12. The estimate for the slope is 9.4905. Right? In theory, I could use that equation to generate a prediction for the underlying trend. Right? Again, this is deseasonalized trend for any time point t. Okay. So if I wanted to generate an estimate for time point 37, I would just plug 37 into that equation, right? I would just do 9.4905 times 37 plus 380.12098. Right? Now, of course, finding the actual prediction interval is not that easy. I can generate the prediction easy enough, but the interval is going to require some pretty hardcore hand calculation on my part, or more easily, right, SASS's help. That CLI statement gives me some additional output, and the additional output's on the next slide. All right, so here's the additional output. Now keep in mind, right, we know this from 512, right, to get that that prediction for time point 37, I would have to make sure that my original data set, right, that decomposition data set had a 37th observation where t was set to 37, but y was set to missing. Right, and that's what I see there at the bottom, right? I see time point 37. It says y variable for 37 is missing. It doesn't show us the t awkwardly, but the t was set to 37. And so, right, you could go back again, a good exercise, right? It's very easy. I know, it's broken record lecture. It's very easy to like sit back and passively listen to me and passively watch these slides just kind of scroll past. And if I'm doing my job well, it hopefully feels like it's making sense as it's happening. But just because it's making sense doesn't mean that it's imprinting itself upon your brain. To make things imprint upon your brain, right, it's up to you, unfortunately, right? To imprint it on your brain, it takes action. And I can't, of course, I'm not a puppet master. I can't pull your strings and force you to action. I could just lecture you every so often that you should be doing that. Right? So I would encourage you, right? Where's that 731.9696 coming from? It's coming from the regression equation on the previous slide. I would suggest going back, plugging in the 37, taking some action, seeing it for yourself. All right? So that's my estimate for the deseasonalized data. There's some error associated with that prediction, and that's embodied by that prediction interval, right? The prediction interval goes from what? From 704 to 758. Now keep in mind, right? So let's think for a second. Our goal is what? Like so we're basically saying that if seasonality was not in play, I would expect 731 units of sales. However, seasonality is in place. So my actual prediction is not going to be 731, right? I'm going to have to do what? I'm going to have to take that deseasonalized prediction and I'm going to have to, right, this is where I would use the term seasonally adjusted. I am going to have to apply that January effect, right? And if I remember correctly, that January effect was very close to 0.5, wasn't it? So it's basically saying, right, if seasonality wasn't a thing, I would expect 730 sales. However, right, and we'll see this in a future slide, because it's January, people aren't drinking Tasty Cola in January. New Year's resolution. Giving up my Tasty Cola, it's just too addictive. And so instead, because it's January, I'm going to expect half of those sales, right? So I'm going to expect something like, oh dear, 365 units of sale. All right? So let's keep that in mind, right? That we're working on this deseasonalized units right now, which is not the units that we ultimately want to be in. Now, something we need to make note of now, we need to look at that prediction interval. The prediction interval goes from 704 to 758, which means the margin of error is what? The margin of error, and again, this is kind of like 512 review. If this doesn't make sense to you, you should come talk to me, because this is kind of like a 512 idea. The margin of error, I can just do 758 minus 704. I could look at the difference between those two numbers, right? So that's 54. And I could divide that by 2. So 54 divided by 2 is 27. So my margin of error is going to be about 27. That's something I could hopefully see. That's not like a time series idea. That's a 512 idea. All right? So what am I observing? I'm observing two things. I'm observing that my deseasonalized estimate for sales is 731, and my margin of error for that is about 27. Okay? Now let's take this information and generate a prediction for actual sales. Oh, here we go. So just like I said, so step 1, we got to reseasonalize our predicted value. So 731, but because it's January, I multiply that by my January effect, which if I go back to the outputted data was 4.49327. So because it's January, I expect to sell 360 units. I take that margin of error for the deseasonalized prediction, right? And I already told us it's the 758 minus 704 divided by 2. That gives us, I said 27, but I guess more accurately it's 26.7492. I apply this margin of error to the reseasonalized predicted value. So I do the 360.71 plus or minus 26.7492, and that gives me a prediction interval of 333 to 387, right? So I would say that we're 95% confident that the actual sales for January of year 4 will be somewhere between, I guess I should round that up to 334 and 387.5. You might say 0.5 units doesn't make sense, but our units are in hundreds of crates, so right, it actually does make sense to have something fractional. All right, excellent. So that's everything in a nutshell for the multiplicative process. I'm going to go into less details with the additive process, because it's really the same thing. It's just our model, instead of being a product of 4 terms, our model instead is the sum of 4 terms. And instead of dividing to remove terms, we instead will subtract to remove terms. Otherwise, everything's pretty much the same, right? So when would I use an additive decomposition model? I would use an additive decomposition model anytime that my scatter plot seems to exhibit constant seasonal variation. All right. Steps 1 and 2 are the same. I'm going to compute moving averages just like I did before. If my L is even, I'm still going to have this kind of awkward thing where my moving averages are like straddling 2 time points, and to fix that, I'm going to create a centered moving average. These centered moving averages, instead of being a best guess for trend time cycle, now they're a best guess for trend plus cycle. I can now generate an estimate for seasonality plus error by taking my original Y and subtracting the estimate of trend plus cycle. Now, trend plus cycle was estimated by CMA, right? So if I take my Y, in the multiplicative model, we did Y divided by CMA. Here, I'm doing Y minus CMA. And that gives me an estimate for seasonality plus irregularity. I can get an average for the seasonal terms just like I did before. I normalize it a little bit differently with my goal in this case to make all of the seasonal values sum to 0, right? So in multiplicative, I want them to average to 1, right? Because in a multiplicative model, like some are above 1, some are below 1, but we want them to sort of on average be 1. In an additive model, some are above 0, some are below 0, but we want them to average to 0. Right, once we have our seasonal estimates, we deseasonalize. Before, we would do y sub t divided by Sn. Here we do y sub t minus Sn. We then, just like before, we plot the deseasonalized data. We look at it to try to estimate the trend. We fit that trend using ProcReg. Again, like very, very, very similar. And then the leftovers are handled pretty much like before. If I want to generate a prediction at some time point t, if I have a cycle, then I would do the trend plus the seasonality plus the cycle term. More likely, I don't have a cycle, and so my trend is just going to be my estimate, my y hat, right? Y hat's going to be an estimate or prediction for some time point t is just going to be the trend plus the seasonal component. Just like before, we can generate prediction intervals by finding the appropriate margin of errors on the deseasonalized data from ProcReg and SAS. So that approach is the same as before. Right, so again, like it's like, what was that? Maybe like 85, 90% the same. And the differences become even more academic when it's essentially we're using SAS to do it, and to change it in SAS, we just do, instead of mode equals multi for multiplicative, we just do mode equals add for additive, and then SAS will just spit everything out just like before. All right. So there's our multiplicative model, which is of the two the most common one. You typically do tend to see either increasing or decreasing variation. Constant variation is relatively rare in practice. So I emphasize the multiplicative model, one, because it probably occurs more frequently, and two, because it's a little bit more unique to us. The additive model, right? Additive models we should be more comfortable with, just because, all right, all of our models in 512 were additive models. Now big picture, like where did decomposition models fit in sort of like the big picture of time series? This process of deseasonalization is very commonly used in terms of like government statistics and government analytics of government indicators. And with this in mind, it is possible. You could definitely go deeper and extend these critical concepts to make like to make models that more accurately represent like everyday realities. Just a few examples, right? We could adjust this. We could adjust our decomposition model to accommodate like different business or trading days per season, right? So if you're looking at like stock market or stock prices, just because the stock market doesn't trade on Saturdays, Sundays, holidays, things like that, you're gonna have a different number of trading days on maybe April than you will on March. You could also like accommodate things like important days falling in different seasons, right? So like Easter can sometimes be in March, sometimes be in April, right? So Easter sometimes is in the first quarter, sometimes is in the second quarter. You can extend it and come up with like some pretty robust like methodology for detecting outliers. You could also allow, or we talked about one of the restrictions of the models we looked at is that your seasonal components are not changing with time, but there are more advanced seasonal decomposition approaches that do allow for that. And then you might have noticed when we were looking at the outputted data, when you looked at that center moving average, there was a lot of periods, right? There was a lot of missing data. So you typically lose time points when you compute moving averages. If you think about that, that should hopefully make sense to you. But there are ways to kind of get around this and maybe in some way interpolate some of these missing time points to kind of give us some extra information to work with. So we could go deeper. I think for this class, it's a little niche to do so. You're going to be doing some presentations, so maybe something to think about. If seasonal decomposition is something you're interested in, if the application of statistics to like government estimation, census type data is of interest to you, then maybe you could do a presentation on some of these extensions if you are interested in that. I just think there's more valuable things we could be spending, the rest of our class time with going forward. To do a lot of those things, a lot of what I just mentioned in the previous slide can actually be done in SAS through something called ProcX12. Um, a good reference on ProcX12 is Practical Time Series Analysis by SAS. That book goes pretty deep actually into like all the different bells and whistles of that proc and how you can do some of that stuff in the previous slide. If you're more interested in some of like the theory that's been going on and been developed, there's another reference for you. So again, if you wanted to do a presentation on this, right, those would be good resources for you.